So continuing on through the notes here, we have kind of another example of this sort of projectile motion type problem. It's a little more complex, but really nothing new here in terms of concepts, right? It's just now that its initial velocity is going to be provided by it being accelerated through some parallel plates to begin with. So this negative charge here, it's not an electron. Be careful. Don't just see negative and assume electron. You can have things with a negative charge that aren't necessarily just an electron. Okay, they just have excess electrons. So this negative charge here is going to be accelerated through these plates, right? Because of the potential difference, be accelerated through to here, and then it's going to travel through these parallel plates and eventually move up. And it looks like they've set it up so that it will just barely clear, but let's read on to make sure. So the diagram below is of a charged sphere with a mass of 1 × 10⁻27 kilograms containing 4 excess electrons. Okay, if it contains 4 excess electrons, what does that tell us? If it has 4 extra electrons, that means it has 4 more electrons than it does protons, right? So that means all the electrons and the protons cancel out, and then you have 4 more electrons left over. So what would the charge of something like that be? Well, it would have the charge of 4 times the charge of an electron, or the elementary charge. And since electrons are negative, it would have a charge of negative 4e, where e is 1.6 times 10 to the negative 19 coulombs. Okay, so that is Q of this little guy here. Okay. What is this question actually asking us to do? It's asking us to draw and label all force and field vectors, including reasonable relative magnitudes. So let's go ahead and do that. So we're going to assume this is down, okay, that we're not viewing this from above, just so we can think about gravity a little bit here. Okay, so assume we're looking at this from the side, not from above, so that this is down towards the floor and this is up towards the sky. So that if that's the case, this does have a gravitational force acting on it. If I wanted to be reasonable with the magnitudes, it's kind of a tall ask by this, because I bet, right, looking at this potential difference, right, that's not going to be very big compared to the electric force. So let's make clearly the electric force be much bigger. Okay, that's still probably not going to do it justice. We'll see when we actually calculate it, but I bet the electric force there is even much longer, probably so much bigger that we couldn't fit it on this page compared to if that's my force of gravity. Now, in between the plates here, let's look. What forces are acting on this negative particle? And so it's left this electric field, hasn't entered this electric field yet. So would there be an electrostatic force acting on it? And the answer is no, right? It's not in an electric field here. There's an electric field in some direction here, perpendicular to the surface of the plates. There's one here, perpendicular to the surface of the plates, but here there's nothing. There's no electric field here. So what would it feel? It would feel just that tiny force of gravity. Again, probably so tiny that we're going to end up ignoring it, but it will ask us to calculate that in a second here. Okay, now let's also draw in our negative charge once it's here. Okay, maybe I'll use black. So let's draw our negative charge once it's in here. What forces is it feeling? Well, look at how its motion has changed. It's gone up, right? So it's gone from moving perfectly horizontally to now suddenly having a vertical component to its velocity. So it is accelerating upward in the y-axis, right? So there must be some kind of force pulling it up. Now, it still has mass, so it's still going to feel that force of gravity. But again, I bet when we do the calculation, we're going to find that the electric force looks way bigger than the gravitational force. Now, I keep saying I bet. I kind of know how we're going to do this, but reasonably, within reason, always is a good time to assume you can ignore gravity, okay? But let the question tell you that. Don't always just assume. Most questions will honestly end up telling you to ignore that force of gravity anyway. Okay, now we've arrived at what I said. Within the horizontal plates, so that's these plates, right? These horizontal plates, would it be safe to ignore the force of gravity and justify your answer mathematically? So how are we going to do that? Well, to know if it would be safe to ignore the force of gravity, we have to figure out how big is it compared to the electrostatic force. Is it going to be basically nothing compared to the electrostatic force? Okay, because most times it will end up when you subtract the force of gravity from the electric force or add it if they were in the same direction, you'll end up not even noticing on your calculator because it's so much smaller. But let's just see. So we have that Fe, okay, for between two plates. Let's start with the equation as it appears on your formula sheet, right? What do we know? We know the voltage across these plates would be 9 volts. Okay, we know their separation distance. So with that, with those two pieces of information, we can get that the electric field, right, essentially now is a known value, or it's very easy to get, okay, because we have those two quantities. And what are we looking for? We're looking for the electric force. So we have to relate the electric force to the electric field through some equation. And luckily we have this guy, right? The electric field is defined as the force it would feel per unit charge within that field, okay? So setting these two equations equal to each other, since they both equal the electric field, okay, well then Fe over Q equals the potential difference divided by the separation distance between the plates. And then since we're looking for Fe, let's solve it for Fe, obviously. Okay. And we have that. The electrostatic force here will be equal to the potential difference across the plates, which would be 9 volts, or 9 joules per coulomb. Okay, actually I'm going to write it as joules per coulomb, times the charge, and we've been told the charge is 4 times the charge of an electron, so because it's 4 excess electrons, so 4 times 1.6 times 10 to the negative 19 coulombs, and we're going to divide that by the separation distance, which we're given as 0.020 meters. Okay. And when you plug that all in your calculator, you should get electric force is equal to 2.88 times 10 to the power of negative 16 newtons. Okay, so yes, a small number, right? But let's check in on our gravitational force here. So this is an old calculation from physics 20, right? The force of gravity that anything feels will be equal to its mass times the gravitational field it's in. Let's just go ahead and define up as positive, down as negative. So that means our gravitational field will be negative. And so Fg will equal the mass of this particle, which we were told was 1.00 times 10 to the negative 27 kilograms times, we're saying down is negative, so the gravitational field here would be negative 9.81 newtons per kilogram. Okay, kilograms cancels with kilograms, giving us that the force of gravity will be, well, negative 9.81 times 10 to the negative 27 kilograms. Okay, so let's compare those two forces. We've got, yes, gravity is pulling it down a little bit to the power of negative 27, though, versus to the power of negative 16, right? So again, this number, if you subtract this from this number, you won't even notice. Your calculator literally won't even pick it up. That's too many digits down the line for it to even notice that something has happened, okay? So essentially, the force of gravity is a non-issue here, okay? Let's just go back a bit. I just want to do some unit analysis on this. We've kind of been neglecting that side of things, but if I have joules per coulomb times coulomb, well, coulombs on bottom, coulombs on top, that cancels out. Then I have joules over meters. Well, remember, a joule, I always think of it in terms of kinetic energy. That's the one that comes to my mind easiest. It's kinetic energy is mv squared over 2, but the 2 doesn't have units. So we'd have kilogram meters per second squared. Sorry, meters squared per second squared, because the v gets squared, the whole thing, the meters per second, divided by meters. So the squared cancels with the meters on bottom, giving us kilogram meters per second squared. And hey, that's a mass times an acceleration. That is a Newton of force. Okay, good. So just doing the unit analysis for that, just to kind of check in. It's always a good way to go back, check your work, check your manipulation. see if your equations are actually valid. Okay, so here it's asking us to annotate. Oh, I guess we should answer the question. Is it safe? Yes, it's very, very safe to ignore. Yes, safe to ignore, right? That's not going to be an issue. Okay, annotate the diagram, which just means write directly on it, the diagram to indicate what physics principle we involved with the mathematics in each section. Okay, so we got to be careful here. Yes, all physics principles are valid. That's why they're principles, right? They're kind of always true. There's nothing ever, they're never violated or anything, but do we actually use them? Okay, do we actually care about them? Are they going to be relevant to the math? So let's go up to our diagram. And let's start at the beginning. Seems like a good place to start. Here, what physics principles are going to be used between these plates? Okay, so which physics principles even apply here? Well, physics principle number 1, non-uniform motion, does apply here because there's a net force, right? So there is going to be some accelerated motion. However, it's not really going to be that useful to us. And I say that because we don't know the distance across here, okay? So in theory, we could kind of have used the same equation we used here. And if we knew the distance it had to cover and we knew the force it would feel the whole time, we kind of could use it to get the final V there. However, there's A, an easier way, and B, a way that will, well, kind of actually work here, right? We could use physics principle number 5 here, I should say. So physics principle number 5 to get the V, that's the speed. I shouldn't put a vector on it because it will be speed since we're using energy, right? We'd have to interpret our diagram to know what the direction would be. But if we do that, then we can determine the change in energy this would go through and then set that equal to the kinetic energy it would gain, right? So what I'm talking about the fact that the voltage equals the change in energy over Q, right? And then set that change in energy equal to the kinetic energy gained. So the potential electric energy it will use there, the potential electric energy it will lose there, I should say, would become kinetic energy. And then at that point, since we have mv squared over 2, we can solve for v and figure out what its velocity final after leaving the plates would be. And then that velocity final would become our new velocity initial over here. Let's think about what physics principle is relevant between the plates. Okay. Now, between the plates, okay, this is relevant. Physics principle number 0, that's uniform motion, Newton's first law, right? It's just kind of coasting. Yes, there is a force of gravity, but as we've kind of seen, it's pretty much irrelevant. So essentially, that's uniform motion. It's relevant. Does it matter for the math, though? No. Once we have the V here, I guess we kind of could say we use it to safely assume that it will have the same V here. However, we really are not going to set up any equation. We're never going to do any calculation on that. We kind of just use it to make sure we can sleep easily, knowing that we solved it, knowing that we were safe to use the V that it ended up with here as the V that it began with here. But now in between the plates, what are we going to use? How are we going to determine, or how are we going to analyze its motion here? What physics principle is going to be relevant? I'll let you think for a sec, but the answer would be physics principle number 1, where F net does not equal 0. Okay, in that case, we actually are going to use. We have to figure out how is it going to move, right? What's its acceleration going to be? Okay, and yes, technically it's Fe plus Fg, although as we know, Fg can probably be ignored, right? But once we know its acceleration, hey, we know its distance that it's going to cover. We even know its Vi. That's enough information using our kinematics equations from physics 20 to analyze its motion for pretty much any purpose we might need to. Okay, let's go back down, see what's next. 3 students calculated the electric field between the horizontal plates. So again, we're looking at the same horizontal plates that we were asking about earlier. Comment on the validity of each calculation. So basically, did the students do it right or wrong? Okay, let's look, again, actually, I kind of want you to do this on your own. Think about it, look at it. Is every student right? Is every student wrong? Did anyone, or probably most likely a combination of the two? Okay, let's look at the first one. So they said the electric field magnitude was equal to 4.5 volts over 0.01 meters. So let's go look at our diagram and see, okay, where are they pulling these numbers from? So we look here, 4.5 volts. Okay, well, the entire voltage is 9 volts. So they're talking about half of the voltage, half of the potential difference. Okay, nothing wrong with that so far, as long as, let's look at their distance. So again, we're comparing this different applications of this equation, right? Nothing wrong with what they've got there, but so far with the voltage, let's see about their distance though. Okay, they used 0.01 meters instead of 0.02 meters. So they used half the voltage, half the potential difference, but they also used half the distance across. So is that valid? Yes, it is, right? Because at this point, the joules per coulomb needed to continue across would be half the amount. If you've already lifted something to here, you've now got to put in you've now put in half the total amount you would have to put in to get to there in terms of joules per coulomb, right? So if you go half the distance, you're going to have to put in half the energy per coulomb. So that is fine. As long as you use half of both, you're good. Let's look at the next one. They did 9 volts and 0.02 meters. So again, up to the picture, 9 volts, that's the entire voltage. So they are talking about the entire potential difference between these two plates. And then they use 0.02 meters. So they use the entire distance. So is that okay? Are they allowed to do that? Do those match? Right? And since they use the full voltage and the full distance separating the plates, yes, that's absolutely fine. What about this one? They use 9 volts. As we know, that's the full potential difference all the way across, but then they use 0.01 meters. That's half the distance. So they used the full voltage, and then they used half the separation distance. Is that okay to do? And the answer, right, is no, that's not okay. Those don't match, right? We go back up here to our diagram. They're saying that to go from here to here, you would have to use 9 joules per coulomb. But we know that's not true, right? We know to go from here to here, you would have to use 9 joules per coulomb. So that does not work, right? So as long as they match, you're good. So that's half and half. So nothing wrong with that. That's all of it, or full and all of it. So that's good. Okay, you could do a third and a third. You could do a quarter and a quarter. You could do 5/8 and 5/8, whatever floats your boat. What you can't do is mix them. Okay. Now it says here, the curved path of this particle is not a circle. This is why you use XY axis separation in kinematics to solve rather than circular motion. Why is this so? Okay, now this might seem a bit weird, but we are going to get into cases where we do actually end up using circular motion when we go into chapter 12, okay? So it's important to right away lay out the foundations of why these are different. So why is this kinematics equations, right? And why do we separate it into XY axes instead of using circular motion? Okay, imagine these plates were kind of infinitely far apart, right? So, or at least much farther apart than they are now, okay? Maybe we can even draw that. Way farther apart. And they're also way, way longer, okay? Way, 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 way longer. I'm gonna try and simulate here kind of what would our particle motion maybe look like. So I'll draw it with this color here. Well, would it ever, I'm just going to give myself some more room by starting down here, okay, even though that's not where it actually started. Would it ever accelerate so much that it would, would it ever in the x-axis, would anything ever cause it in the x-axis to actually end up coming back and moving into some kind of circular motion, right? Is there anything in the x-axis causing its x motion to change? And as we've already seen with these parallel plates problems, no, there's not, right? That's why we're using the kinematics. When we drew our forces, look at it. Is anything speeding it up or slowing it down or changing its direction in the x-axis? No, neither of these forces are directed along that axis. So forever and ever and ever, even if these were infinitely separated plates, it would go like that. It would follow a parabola. Okay, it might get to the point where its x component is tiny compared to its y component, but its x component the entire time is the same size, right? Its x component always looks like, let's say, whoops, let's say this, okay? Even there, even there, even there. Why does it look, well, I can't fit it, but you know what I mean? Should be the same size. This should actually be probably a little bit bigger. Why is it starting to look so different? Just because the y component is getting bigger and bigger and bigger, right? Significantly so, to the point where once we get farther and farther, it's going to look like the y component is huge compared to the blue x component. However, the x component is not changing, and it all comes back to the fact that there are no forces in the x-axis. Actually, maybe I'll leave that up. Why not? Okay, so when we go back to our problem here, why is that so? Well, it's what we just said. There are no forces, okay, and therefore no acceleration. Maybe I shouldn't say there are no forces. There is no net force, right? There could be forces in the x-axis. I mean, there's not in this case, but what's really important is that there's no net force in the x-axis. There are no net forces and therefore no acceleration in the x-axis. So if you're going to move in a circle, you have to, at some point, accelerate in the x-axis. Watch as I draw a circle here, right? I'm accelerating the x-axis right now. And look, here in the x-axis, I'm actually moving the opposite way I started. The only way to end up moving in the opposite way than I started is if I accelerated at some point, okay? As we know from physics 20, this thing is constantly accelerating radially inward. So there, that's a y acceleration, but there, that's a y acceleration. There, that's a y acceleration. Or sorry, there, that's an x acceleration. There, that's a y x. Some combination of the two, some combination of the two. So to move in a circle, you require x forces, okay? They can change from x to y and some combination of the two, but they can never, but there will be x forces present, I should say, okay? So there are no net x forces and therefore no net acceleration, okay? So why are we using projectile motion? All forces present are in y-axis, causing what we would call parabolic motion. Parabolic, does that word look familiar? Well, it comes from parabola, right, from math class. This follows a parabola. Half a parabola, sure, but still, it's a parabola. Okay, it gets steeper and steeper and steeper because it's going faster and faster and faster in the y-axis, but its x motion is actually not changing, causing parabolic motion. And we'll just remind ourselves, just like when we did projectiles in physics 20. Okay? Now, we keep kind of harping on that x and y thing, but realistically, take these plates right now and turn them in your head 90 degrees so that instead they look like that. Okay? Well, in that case, there would be no y forces. I mean, gravity would be there, but again, 99% of the time we can just ignore gravity. Okay? But in that case, we would treat the question essentially the same, except now it would kind of be flipped to what we're used to in the x and the y, right? Now there would be no y forces, and the only really relevant forces would be the x. Would anything really look different for how we approach it? No, except for the fact that what we usually do in the y, we are now doing in the x, right? So if you can get over switching those letters, then nothing has really changed at all. So here we have yet another projectile motion type problem, okay? Again, this is where I would usually say to you, do this on the whiteboards, okay? So I'm going to say, pause the video, try it out, okay? And then if you feel good, skip to the end, see if you got the right answer. But then if you're stuck along the way, you always have the option here to follow through with my solution. But again, try it on your own, okay? So, a beam of electrons is incident on a region containing a uniform electric field as shown below, okay? That was nice of them to tell them that. They didn't have to tell us. We know that between two oppositely charged plates, the uniform field, two oppositely charged parallel plates, I should say, the electric field is uniform. Okay, so the electrons in the beam each have a speed of 4.5 times 10 to the 5 meters per second. While in the electric field, the electrons accelerate towards the top plate. Okay, that makes sense. They would, right? They're electrons. They're negative. They're going to move this way up to the positively charged plate. Okay, so they were very nice here. They even told us, hey, make your measurements. You will want to make your measurements on the diagram. They may, like I said, often just say, this diagram is to scale, and that's your clue. Okay, I have to pull out the ruler. I have to actually make measurements. Okay, so let's first see what kind of measurements we might be wanting to take. We could kind of just go ahead and start making some, but let's just plan some stuff out here. So based on our measurements and our calculations that are going to come, the strength of the uniform electric field, so the strength of the electric field, we're looking for the magnitude of the electric field in the region is blank. So we're looking for the magnitude of the electric field. Okay, now we have a couple equations for that, right? We have kq over r squared, right? But that's usually for a point source. Really kind of no good to us here. We have an electric field is equal to the potential difference over the separation distance. Usually that is a good place to go in our head with a parallel plate equation, right? That is a parallel plate problem. That's actually a great place to go, okay? And we can even use our measurements to get the separation distance. However, there's nothing in here at all about voltage. So that's not going to be my go-to, although I don't believe it would be an impossible thing to use. I'm just going to take a different, kind of a more efficient approach. I believe you could still use that one. I haven't solved it through, but it could work out for you. Okay, I'm going to think, well, what kind of problem is this looking like to me, right? This is looking to me like a kinematics type problem, right? And so if it's a kinematics type problem, that means I'm going to have to think about the forces causing this to accelerate, right? I'm thinking about accelerations and what causes an acceleration, a force. And so I'm kind of linking it now in my mind to this equation, right? If I can think about the electric force involved here, right? Sorry, if I can think about the accelerations involved here, like in a kinematics problem, well then I can get the forces involved, and then I know the charge of an electron, so hey, I have the electric field. So that's kind of going to be my game plan here. Okay, so how do we approach a kinematics problem like this? Well, we are able to make measurements. Okay, whenever we're looking at something like this, we kind of need to split it up, right? We need to think about the motion in each axis separately. So let's just make our table. Where do we have some room? We kind of don't have room. Well, okay. Let's make the best we can on this tiny little space here. Oh boy. Okay. Now I'm not going to pull out the virtual ruler. I'm going to go ahead and use the measurements I took on paper. It's just because that will A, better match your notes, and B, better match my solution that I have worked out here already. Okay, so I don't have to recalculate everything. So if I'm looking at that distance there, sorry, I should first make my table, right? What are always the 5 variables? D, VI, VF, A, and T, right? The 5 kind of kinematics variables. I'm just going to give myself more room on the y-axis there. That's not going to be enough. Probably still not going to be enough, but we'll make do. Okay, dy, diy, dfy, ay, and ty. Okay, now, when I go to say what's dx, vix, vfx, ax, and tx, dx, no, I'm not just told it, but I'm told I'm allowed to measure it, right? So that's actually what I was starting to do here. So when I measured it on paper, I got this horizontal distance traveled by the electron beam, I got it to be 4 centimeters. So your answer may be slightly different, but that's what I'm getting. Okay, so that is, that is 0.04 meters. Okay, now the ix, right, they actually told us that the initial component of the initial x component of the velocity is, it's all in the x, right? So vi is vix, and it's 4.5 times 10 to the meters per second. So put my y right there, I'm about to write here, so 4.5, sorry guys, this is tiny, times 10 to the 5 meters per second. Ooh, that's small, sorry. Okay, now what's causing it to change its velocity in the x-axis? What's causing it to speed up? What's causing it to slow down? Okay, a little bit of a, I guess, trick question, but not really, right? Can't get tricked, you know your stuff. That is, there's nothing, right? Nothing is causing it to speed up or slow down in the x. Where is the force here? It's up and down between the plates, okay? There's nothing to do here horizontally. So what does that mean for VFX compared to VIX? It doesn't change. 10 to the 5 meters per second. Why am I allowed to say that? How do I know that? Because the acceleration is 0 meters per second squared. Why is the acceleration 0? Again, because the force is 0. Okay. Now Tx, do we know it? Nope. But we know it'll be the same as Ty, right? Often in these kinematics type problems, time is kind of the key to solving it, right? Just because that's the thing that's going to jump over from our x to our y. That's kind of the bridge that connects these two axes that we need to analyze. Okay, now what about our y distance? How far does this thing move in projectile motion in the y-axis? Well, again, they told us to measure, so we can measure that, okay? I'm getting, when I measure, that is 1 centimeter. Okay, so if we were doing an off-a-cliff question and you flip your head upside down and look at this, that means the cliff, so to speak, would be 1 centimeter high. Right? Just kind of connecting it back to what we did in Physics 20. So dy 0.01 meters. Now VIY, how quickly is this thing moving initially? What is the y component of its velocity initially? Well, it's not. It's coming in horizontally. Okay, so VIY, 0 meters per second, just like an off-the-cliff question in Physics 20. VFY, we do not know it. Maybe we'll need it, maybe we won't. Let's figure that out. We'll figure that out later. Okay, AY, no, we don't know it, but remember, we can figure it out, right? Or we kind of will need to with AY equals F net over M, right? So no, we don't know it, but it probably will be, it definitely will be, because where are we going with this, right? We're trying to eventually get the electric field. Okay, then the time in the y-axis, we don't know, but we know it's the same as the time in the x-axis. So let's take a second, think about this. What's our plan of attack here? Okay, so what are we interested in? We're interested in, realistically, the y-axis. We want to know more about the forces so that we can know more about the electric field over here, right? Our goal is to eventually get this, the electric force felt by the electrons, so that we can get the electric field the electrons are in. So we need to know more about the y-axis. And the problem is, do we have enough information here to just right away get acceleration in the y-axis? We are close. We've got D, we've got a VI, okay, we've got an A and a T. However, sorry, we've got a D, we've got a VI, we want an A, but we don't have a T. So we don't quite have enough ingredients to use one of our kinematics equations, one of our 5 kinematics equations from Physics 20. However, let's look over here in the x-axis. We know how far it went in the x-axis. We know how fast it was moving. Can we figure out how long it would take something to move that far if it's going that fast? And yes, we can, right? We've got a uniform motion situation here, so they really did not give us much room here. How about, let's just make a new page and I'll come back and forth between these. Okay, so a new page. Let's just say, call it step 1. Find. I'm going to call it Tx, even though it's really just T. Tx is Ty is just T. Okay, so since it's uniform motion, you could use the other kinematics equations, by the way, but when acceleration is 0, all of the other kinematics equations end up becoming this guy anyway, really. Okay, so Vx equals dx over Tx. So then Tx equals dx over Vx, just multiplying and then dividing. So that equals the distance it's traveled in the x, as we measure on the picture, is 0.04 meters, and its velocity was 4.5 times 10 to the 5th power meters per second. Okay, so how much time would it take something to go 4 centimeters if it's moving that fast? Probably not a lot of time. That's very fast, and it's not that far to go. So I got 8, sorry, not a 6. I got 8.8 repeating, basically. 8.888889 times 10 to the negative 8 seconds. Yeah, it makes sense. It's going 450,000 meters per second, and it only has to go 4 centimeters. It's not going to take very long to do that. Okay, great. Okay, now we got t. Now we got t. We got tx, which means we got ty, right? We got tx, which means we got ty. So we got t, that means we got ty. Now let's look at this. We've got a dy, we've got a diy, we've got a ty, and what do we want? We want acceleration in the y-axis so that we can then figure out the force in the y-axis. If we have the force in the y-axis, then we have the charge, then we can get the electric field. Always good to kind of look at your roadmap as you go. Sometimes I know in physics we're just kind of throwing stuff at the wall and seeing what happens, and eventually we get kind of inspired, but it's also nice to every now and then, not every now and then, whenever you can, realistically try and plan ahead, see where we're going, think about it. Okay, so now we got a D, VI, an A, and a T. If you look at your blue formula sheet, right, you'll probably notice that, or you might decide that the best way. And again, there's, just like in Physics 20, there's more than one way to approach every kinematics problem, okay? You don't have to do it exactly the way I do it. We got 5 kinematics equations. I'm just kind of going with the most efficient, where I'm not finding other stuff along the way that I'm not going to end up needing. So find the acceleration in the y-axis. And again, we're going to use dy equals viy t plus 1/2 at squared. Okay, and again, we said in the y-axis, whoops, not that whole thing. And the y-axis of this whole thing is 0 because VIY is 0. Okay, and so dy equals ayt squared over 2, and then we're solving for a, so we'll multiply both sides by the reciprocal of this kind of expression here, so times 2 to cancel out the 2's, and then divide by t squared. So times 2 over t squared, and we have that the acceleration in the y-axis is equal to 2 times dy divided by t squared. So the acceleration in the y-axis is equal to 2. We measured on the diagram that the vertical distance traveled in the y-axis is 0.01 meters, right, or 1 centimeter, divided by the time squared. So what did we find the time to be? It was 8.8889 times 10 to the negative 8 seconds. Okay, great. So now we've got, squared, don't forget to square that. Okay, so now we've got that the acceleration in the y-axis, or at least I got it to be 2.5312 times 10 to the 12th power meters per second squared. So a very fast acceleration. Okay, a very large acceleration, but that makes sense. We've got a little teeny electron. It doesn't have a lot of mass. It's got charge. Okay, and we all know the electrostatic force is relatively strong. Okay, at least stronger than the gravitational force. Okay, great. So now we've got the acceleration. Right? Let's go back. Look at our roadmap. What are we trying to do here? We're trying to figure out the electric field. We've got the acceleration. Okay, so can we figure out the force that must have acted on an object with that acceleration? Okay, well, let's see. So we know it's accelerating. We know its mass. Okay, I think we're actually good to go, right? Step 3, find the electrostatic force that must have been acting on that electron if it accelerated at this rate. So, Newton's second law, A equals F net over M. Let's just be safe and include gravity, although I'm sure you probably know how this is going to go. Okay, the electric force plus the gravitational force, just based on this acceleration alone, right? That's paling. That's making gravity look pathetic, right? But let's just see. Fe plus Fg over the mass. Okay. Remember, don't lose sight of what we're trying to do here. We're trying to find the electrostatic force. Okay. And so the multiplying both sides by m, we have F net equals ma, which is basically just another way of saying Newton's second law. just not the way it's written on your sheet. And then subtract the force of gravity. Okay, let's go ahead really quick and define our directions. We'll say that's positive, that's negative. So gravity here is going to be negative, which means gravitational field here is going to be negative. We have there that the electrostatic force is equal to ma minus mg, just replacing fg, get mg. We could even say m times a minus g if we wanted to, save ourselves a few button presses on the calculator. What is the mass of an electron? On the back of your formula sheet, it's given as that, right? As we learned Millikan also determined recently. 9.11 times 10 to the negative 31 kilograms times what's its acceleration and which way is its acceleration? Is it a positive or a negative? Okay, so we got a positive, but to be honest, I've been a bit reckless here. Let's go back. If I'm defining up as positive, okay, and down as negative, good, okay, yes, that does make sense. It's accelerating upward for sure, right? So that acceleration caused by the electrostatic force should be positive, and G, the gravitational field, should be negative. So A minus G, where A is this huge acceleration we found it to have, okay, 2.5312 times 10 to the 12 meters per second squared, 2.5312 times 10 to the power of 12 meters per second squared, minus, if the gravitational field is negative, okay, so minusing negative, yes, does that make sense? Because not only does the electrostatic force have to be strong enough to accelerate it at this rate, it's also got to overcome the 9.81. So we're kind of adding that. We're minusing the negative because it has to also overcome that, right? If we were to take it away, that would be saying that the Fe would need to be weaker, but the Fe doesn't. It needs to be even stronger to overcome gravity. Although, as we'll see, or as you're probably seeing, even just looking at those numbers, gravity is pathetic, right? Compared to this acceleration due to gravity is nothing. So I'm getting the same you would have got if you had ignored gravity. I'm getting 2.3059 times 10 to the negative 18th power newtons. Okay, now what did we set out to do? We set out to find the electric field. So our fourth and kind of final step here, find E. Okay, by the way, force is a vector, so really I should be saying, what is this? What's its direction? It's towards, the force it feels would be towards positive plate. Right, and of course, same goes for the acceleration, towards positive plate. Okay. Okay, so we're going to say that the electric field, like we set out with, electric field equal to the force divided by the charge. Keep in mind though here, how do we define the direction of the electric field? It would be in the direction that a positive charge would feel. So it's actually our force, yes, is towards the positive plate, okay, but is our electric field going to be towards the positive plate? What kind of charge is feeling this force in this problem? An electron, right? So a negative charge. So it's actually that force, yep, it totally would be towards the positive plate. However, our electric field direction is actually going to be towards the negative plate. You should never find yourself saying that the electric field is towards something positive, right? Because that is never the direction a positive test charge would go. Okay, so the electric field is equal to the electric force over the charge. Maybe let's just throw magnitudes on that because we kind of have to interpret in the end what direction is going to be. Okay, so that equals then 2.3059 times 10 to the negative 18th power newtons over what's the charge of an electron? It's negative E. So we don't use the negative because we're just looking at magnitudes, and the negative doesn't tell us direction anyway. 1.6 times 10 to the negative 19 coulombs. Okay, so newtons per coulomb. Good, that's the unit of electric field. So what is the magnitude of the electric field strength? I'm getting to two significant digits because that is what we were given. Okay, also the Scantron thing tells us record 2 digits. I'm getting 14 newtons per coulomb. Okay, if we wanted to remove those magnitudes, even though the question doesn't ask for it, but just for fun, which way is it? Which way is the electric field? Is it in the same direction as the force? Right, as we said, no, it's not. It's actually the opposite, because this force, the thing feeling this force that we've calculated, is a negative charge. So it would actually be towards negative plate. Okay, or, yeah, okay. So what would we put on our numeric response? We would bubble in 14 newtons per coulomb. Okay. Now this question is saying two physics principles must be used to determine the strength of the uniform electric field. Using the numbers on the tear-out data sheet, match the physics principles with the order in which they are used, and note that there is more than one correct answer. That's because there's more than one way to approach a kinematics problem. So what did we do? Okay, well, let's just go look through our thing and see which physics principles are we kind of applying here, right? So here, we're applying uniform motion, right? We're looking at uniform motion. We're looking at motion where F net is 0, okay? That's kind of what we're doing there. So the first thing we use was physics principle 0, okay? Then here, in steps 2 and 3, we kind of used Newton's second law, where F net equals ma, right? Accelerated motion. F net does not equal 0. So in steps 2/3, we used physics principle number 1. Okay. Very common mistake with students is to say, there's charges involved. So this must have something to do with the law of conservation of charge. Okay. Just because there's charges doesn't mean you use that law, right? At no point here did we actually use that to explain ourselves or to do calculations or anything, right? We were really just relying on Newton's laws here. Okay, so what would we put in our scantron here? We would say, first we talked about uniform motion to figure out the time, and then based on its motion we figured out the forces, or the accelerations to get the forces to get the electric field. Okay, and that would be our answer, 0, 1.